Hello everyone, and welcome back to the World Cement podcast with me, Senior Editor of World Cement, David Bizley. In this episode, I'm joined by Professor Theo Hanein, Chair of Construction Materials Science, and Dr Wafaa Borja, Research Fellow at Leeds University's School of Civil Engineering. And our topic? BCSA cements and the work being done at Leeds University to transform them from a product reserved for niche applications into a more mainstream alternative to Portland cement that can play a role in decarbonising the cement and construction sectors. I just wanted to take a moment to remind you to register for World Cement. It's free of charge and gives you access to the latest issues of World Cement, both in print and online. Every issue comes packed full of regional analysis, technical articles, project case studies, and the latest industry news. Simply head over to worldcement.com, click the magazine tab and register today. It's as simple as that. Happy reading. So, as always, we like to begin with an introduction. So, Professor Hanein, Dr. Borja, could you briefly tell us a bit about who you guys are and what it is you've been working on at the University of Leeds?
Hi, I'm Professor Theo Hanein. Please call me Theo. First of all, I'm very happy to be here and grateful for the invite to take part in this recording. My role is I'm chairing Construction Materials Science at the University of Leeds in the School of Civil Engineering. I'm also a UKRI Future Leaders Fellow and Vice President of the Board of the International Society for the Environmental and Technical Implications of Construction with Alternative Materials, or SCOA, for less of a mouthful.
Thank you. And Dr. Borja?
Hi, my name is Wafaa Borja. Thank you so much for the invitation. I'm very pleased to be part of this podcast. I'm a research fellow at University of Leeds, and I'm working with Professor Theo Hanein on the FLF project. So I have a PhD as well in waste recycling and material science. So my expertise is mainly on creating value from waste and transforming industries to become more sustainable and greener.
Excellent, thank you. Well, to kick things off then, Theo, let's start with the basics. What is BCSA cement and how does it differ from ordinary Portland cement, the thing we're used to?
BCSA cement is actually from the family of CSA cements, which is calcium sulfur aluminate based cements, and the B in BCSA stands for belite or balytic because that is the major phase, if you would like, instead of any of the other phases or species in the cement. Now, these cements are not new. They've been used for decades, although in much less quantities than Portland cement, and tailored for very niche applications normally, such as for things like shrinkage or expansion or other requirements. So the chemistry is different, but it's not new. The main phases in a BCSA, I won't go too much into the chemistry here, but are belite and yelamite. And to put that into perspective, the main phases in Portland cement are belite and alite. So we're basically just replacing, if you would like, the alite with the yelamite between BCSA and Portland cement. Now, yelamite has a lot of advantages in that it's rapid set, first of all, and it gains strength very quickly. So that's why we believe it's a good option to continue working on. BCSA offers rapid early strength gain, making it particularly suited for precast components and EN 1504 compliant repair, where speed and performance are critical. Now, the reason I mentioned the standards under which this can work is because EN 1504 is performance-based, whereas for other applications, for the structural applications, we have more, if you would like, chemistry-based standards, which I think are changing slowly but surely. So BCSA in particular has been used mainly in the US and China, as I said, since probably the 60s. And currently, the price is 10 times the price of Portland cement in the US, I think, or thereabouts. And this is mainly because of, obviously, economies of scale, but also in particular the raw material. But still, it's used in applications that require rapid setting, basically. So in airport runways, where if you close a runway for a certain amount of time, you're paying tens of thousands of pounds per minute, It's used by the US Army to quickly rebuild things that have been, for example, destroyed or infrastructure that's needed very quickly. It's used in road repairs in California, but that's also because most of the roads there are concrete, but not only that. In the US, I think every state has its own different codes. But in California, for example, it's specified in the code to be able to be used. So I think it's already very clear that one of the limiting factors of using this is currently specifications, standards, codes. BCSA cements can also have very good performance in marine environments. So marine defenses, or even for the floaters, wind turbines, which we know we're going to need to upscale a lot going forward, and we're going to need a lot of concrete. Actually, it's calculated that the concrete we're going to need per year just to produce the foundations, if you would like, of these wind turbines, of what the goal is, more of the concrete than we can produce currently in the UK, including Portland cement. So we need alternatives. We need, obviously, more manufacturing. And it's not a speculative innovation pathway. It presents a potential transitional material strategy capable of replacing one-day general cement, but in the short term to start to enter the market through applications where it can be used, as long as we reduce the price, which is what we're doing as part of our work here at Leeds.
What is it then about BCSA cement that makes it attractive from a decarbonisation perspective?
Okay, so the main culprit, if you would like, or CO2 emitter in cement is from the clinker. And this is because clinker is mainly produced using limestone rock, so calcium carbonate.
Mm-hmm.
And when this calcium carbonate is calcined into a clinker, it emits that CO2. Now, this represents most of the CO2 emissions from the cement industry, whereas the remaining part is from the energy needed for the fossil fuels used in these high temperature furnaces, and then also some auxiliary electrical, if you would like, components, etc., and transportation within your plants or to where you're going. Now, what the first BCSA from Portland cement is that mainly it requires less calcium in the chemistry. So already from the start, instead of having 80% limestone in your raw meal feed into your kiln, it's around 50 or 55%. That's not the only advantage. There's also advantages because it's made at a lower temperature. But the good thing is it can be made using existing infrastructure, such as cement plants or even lime kilns, right? So there is a lot of capital investments, whether you wanted to take this up quickly, that would be required, or a lot of processing development that would be needed, apart from treatment of the raw materials, which Wafaa will talk to you later about. But overall, I would say before the studies we've made to massively reduce CO2 emissions and the cost and the product we've done, a BCSA was roughly around 30% already less CO2 emissions than Portland cement.
Right, okay.
There are also, in terms of decarbonization, there are also a lot of benefits. Although time is not a functional unit currently when CO2 is being calculated, it's always being calculated by mass. But if you wanted to calculate the CO2 emissions of the time saved and the performance gain, because you get better compressive and flexural strengths, mechanical properties, and you can tailor it for better durability properties, then I think that number will increase exponentially.
Okay, interesting. So the University of Leeds has been carrying out some notable work on BCSA cements. Could you quickly run us through the highlights? What developments have you overseen?
So here at the University of Leeds, through my Future Leaders Fellowship project on green, circular, and smart cement manufacture, we are leading a quite large project on this it's been ongoing since 2021 and now has been granted extension all the way up until 2029. Now, the idea behind this project was, look, this is a great cement. Why don't we make it in the UK, right? Because we didn't produce it here. And the overarching aim of the project, if you would like, is to enable its manufacture in the UK by 2030. And we are already on the path, and they're on time as well. So the main reason why it wasn't produced in the UK was because the UK does not have bauxite, which is the alumina source. Because I said earlier, it requires less calcium, but that means it requires more of something else, which is the aluminum. Now, what's different in our project is we use alternative raw materials, such as waste clays and waste from other industries, such as the water industry or the aluminum industry, which Wafaa will go into with you later about. But the achievements include, first of all, scoping out the raw materials and the quantities available. And I think we have found enough raw materials that can replace currently up to maybe 15% of UK cement. But I don't really think we need to replace any cement because we have more demand that we can produce. So I would say we can produce at least 15% more of this cement currently with the raw materials that we've scoped out. We've done extensive lab testing to get the chemistry right, basically, and also the physical properties. Basically, we've discovered all the underpinning fundamental properties that make it as good as it is, and, will also allow us to tailor it for, obviously, the market. Everyone has an opinion, right? There's always going to be different needs. So we're also developing all that technology where we can use the cement for different needs as well as in different climates. So we've come up with a recipe we're happy with, the first recipe, I would say, and we've scaled this up and we actually made a few tons of this material in a rotary kiln, and we are currently doing the durability testing. And the next phase of the project now, which starts in August of this year, of 2026, we are going to focus on a demonstrator. So obviously, we're going to build something at the University of Leeds, hopefully, and actually build it and use it within 6 hours. Sorry, use it within 6 hours after building. Yeah, the 6 hours doesn't include the building. But yeah, and then involving that also, a lot of work is going to be done on incorporating it into specific standards and codes. This is because you can make something great, but if the policy is not there and you aren't allowed to use it, you can't do it. So that's what a big part of my work over the next 3 years is going to focus on. And I think I have the right project partners on board to help me do that. And then also to increase the TRL as much as possible up to the level where we can also sell the technology and IP to other countries, or to basically achieve what research funding is for, which I believe at the end of the day is a big part of it, is to create jobs and clean economic growth.
Okay, excellent. Moving to you then, Wafaa, one of the things that we've touched on now is that you've been working on the use of locally available waste materials to produce BCSA. So how viable is the approach in terms of both the quality of the end product and, I suppose, the practicality of sourcing sufficient waste materials?
From a sustainability point of view, using waste in cement manufacturing represents a highly promising strategy, both from environmental and economic perspectives. But from an industrial point of view, using waste in cement manufacturing comes up also with a lot of challenges. And we need to see how this waste introduction or incorporation will affect the technological behavior, the technical performances, the environmental impact, and also the economic sustainability, accounting for the balance between the costs and the benefits in terms of energy consumption, in terms of transportations, and so on. So in the context of UK, huge waste or huge amount of waste, such as the salt slag, waste clays, and also the NMP, which is the non-metallic products derived from the salt slag leaching process. So this waste, we are talking here about huge amount of waste, approximately about 45,000 tons of aluminium slag per year only in the UK. So instead of just storing this waste within the industry or the landfill strategies or thinking about the management of this waste, we can reuse them in the production of BCSA cement. And this is the goal of our project. So we are using this waste in order to produce BCSA cement. But as I said in the beginning, this will come with a lot of challenges, and we overcome all of these challenges in the FLF project in terms of materials nature, in terms of the effects of the impurities. And for that, we did like a careful characterization and mix optimizations. They were really essential to ensure consistent quality and performance as well. So our approach in general was technically viable and demonstrated a strong potential for sustainable cement production. And now we are still working on making it more better in terms of long-term durability, and also to support the large-scale industrial implementation.
Okay, excellent. And I suppose following on from that point about viability, and Theo touched on this a bit, but how do BCSA cements compare to Portland cement in terms of things like strength development, durability, and long-term behaviors?
The BCSA cements are now considered like technically viable for many applications, particularly where the rapid strand development and the lower embedded carbon are important. It is very known by its fast setting, so generally it will develop early age strands much faster than OPC, like within 4 hours. In terms of durability, BCSA can perform well in sulfate environments. It often exhibits lower shrinkage and lower heat of hydration, and it may achieve like the chloride resistance and the corrosion performance comparable to OPC over time, as the microstructure will densify with the time. But their early age durability can initially be weaker than the OPC. And in this area, we cannot neglect that OPC benefits from over a century of field data and highly mature standards. So BCSA systems, they have a much shortened service history. So we need to work on this more and more in order to earn the trust of the market as well. And this is the next phase of our project, is to include these standards within the concrete standards, and maybe why not using it in structural applications as well.
Okay, excellent. And what do you see as the most likely applications for these types of cements? Are we looking at niche use cases still, or is there a scope for more mainstream construction applications down the line?
The produced BCSA cements from waste generally, they have already like a technology readiness level between 3 to 4. So this system, they have already demonstrated promising laboratory and pilot scale performance. But for our cements, I think now we can use it as a retail application. And in the future, we can use it also in structural uses. One of the main hindrances to do that is, as I said previously, is that this vendor is not included yet in concrete standards. And this is one of the main goals in our project, is to collect more data and also to include this vendor in the list of concrete standards in the future.
Okay. Now, of course, it's one thing to develop these new technologies and processes, and then quite another to get them to market. So you touched on this a little bit, I just heard just now. What do you see as the main obstacles to commercialization then? Is it standards, costs, raw material availability, or a combination perhaps?
Yes, I agree with you. Many laboratory fundings are not yet entered into industrial scale. And this transition from the lab scale to the market is usually called as the valley of death, because many studies, they failed to overcome this turning point. And the main problem is, I think it's a combination of standards, costs, and also the heterogeneity of the waste. Because, as I said in the beginning, we have to take into consideration how this waste will affect the technological performances. And for this, there is many examples that we can highlight. For example, difficulty in batch design due to the presence of impurities, the release sometimes of harmful gases during firing, the formation of the alkali sulfate rings in the furnace that can sometimes stop the production, as well as the lack of evaluation standards. We can also talk about the market acceptance. So this finished product should respect the market needs and also respect the standards that have already in the market. And we need also, I think one of the main reasons for BCSA hindrances commercialization is, first of all, is the high price and the low availability of bauxite worldwide, because it's estimated that only 10 countries contain about 90% of the bauxite reserves, which justify the high number of research studies on BCSA production from locally available waste within UK and many other countries overseas. And the second challenge, I think it's the heterogeneity of the waste, as explained before. So we'll definitely have supplementary steps in the process in order to energize these hazardous materials. We need also to optimize the mix design in order to obtain a well recipe that will have good performance in terms of mechanical strength, in terms also of durability. So I think it's a combination of all these factors together that sometimes stops the lab fundings to go to the markets level.
Okay, thank you. And Theo, what's your take on this? What is your strategy for overcoming these challenges? Is there, for example, a greater role for government to play in enabling the adoption of these kinds of novel cements?
Basically, my colleague Wafaa earlier mentioned, the valley of death. So I guess the solution is to create the activation energy to cross that valley.
Right.
And that obviously needs momentum. And where does this momentum come from? Obviously, it's by, you can't just do it by yourselves. You need to go out and talk to people and convince everyone, including governments, etc. Now, the way to do this is obviously to disseminate the research in a way people can understand. For example, Wafaa mentioned that one of the key issue of manufacturing more BCSA around the world is the bauxite, and we've replaced that bauxite, right? With many ways, including the salt slag and the non-metallic product, the NMP, that was mentioned earlier by Wafaa. So just as an example, 150 cans of aluminium recycled can make you 10 kilograms of BCSA cement.
Oh, wow. Okay.
Obviously, because you don't need to put that much in it, right? You put limestone, clays, and other things as well.
Sure.
But that's the alumina source, and it's a very good and pure alumina source. And you can see how many cans you can find around. And aluminium recycling is going to go on for the foreseeable future. We need aluminium. It's one of the most abundant chemicals in the Earth's crust. Before I go into policy, supply chain management or confirmation. So, if the cement industry of producing BCSA is going to rely on this alumina source, which is available, but you still need those long-term contracts in place. You still need to make sure that you have that supply chains, that you have long-term contracts between these industries such that they can make a viable business plan over 50 years rather than be worried that one day the supply will stop or something like that.
Sure.
We've been mentioning that the cement is rapid set, right? The labor force, the people who are going to use it on the field, would either need to get some additional training on it. So this is where we have to go out and make short courses and do things to inform about the risks, first of all, but then also about how to use it in the way that, because using a material well or badly also constitutes to the overall CO2 emissions, right? If you're not getting the most out of it, you always want to use the right material for the right application, but then if you're not using the material correctly or you're over-designing, then that's not good. But then also under-design is not good. So I guess what I would like to add is, I think some of this BCSA is already sold in the UK, but obviously if it starts being manufactured at a larger scale, those manufacturers can either provide the service of the training, obviously, or reach out to train people. And since it's a long-term plan, what I would suggest is to go out into schools, colleges, universities, those people who are going to make the workforce of the future, go out and give them some of this material, teach them how to use it, let them already start using it from now. And obviously, it will make an exciting practical class in a school or a college or university to try different materials and see what can be different. And I've already used this approach for a different material in the past, and it's actually very much welcomed by schools and colleges. And you say, okay, they've been using this one material, let's give them a slightly different one and see if they can manage to use it, So now, obviously, we're going to go into one of the main things, which is policy. So obviously, you're going to need more experts in the field here who have, I wouldn't say a long arm or lobbying, but if people aren't aware of this material, which we think is amazing, and we cannot take it to Parliament or get it in the news or start getting those enablers in place, right? Like knowing who to talk to for, starting from a local MP or local schools, but definitely need to get the word out and then join those standards and specification boards, which is what we plan to do. As academics, in the past, you were always just supposed to do science, then somebody can take it onwards from there. But now demands are high, times are hard. The return on investment required is required in a much faster time. There's a different world out there where you have to go and get engaged with, okay, which applications can you use it in? How do we influence the policy? If it's really that good and saves that much CO2 and money, how do we take it to Parliament, right? And then who do we need to talk to, get those specifications done so anybody who wants to buy it can say, okay, this is how it's used. And obviously all the other documents that are required, such as EPDs, environmental product declarations, etc.
Okay, excellent. And then looking to the future, where exactly are we in that process of getting BCSA cements into broader industry use? And what kind of time frame do you think we should be looking at for this process to happen?
As I said, I think, the science required will be done before 2030. Obviously, there's as anything as an end to knowledge, but at least enough to get started will be done, and more will need to be done. Obviously, KRI has already funded a lot of money on this topic and other partners as well, and that funding will need to continue. But I think by 2030, as I said, manufacturing capability will be there and supply chains will be there. And then obviously depends how far and how quickly we get on with putting it in specifications and standards and reaching out to people and marketing. There's a huge world out there after knowing how to make it in the lab to then scaling it up. And even now knowing how to scale it up, if you don't have sales, you might as well turn off the furnace, right? There's a much bigger world out there, which I think requires, people working on the topic that are not just, that are very versatile, understanding the bigger picture and where to stop on improving on certain things and breaking down those barriers that are still in place, which I've mentioned earlier, such as getting the world out there, making a demonstrator, and continue, obviously, pushing the narrative, probably not the right way to put it, but yes, disseminating our work well enough so that other people continue to work on this and take it forward as well.
Okay, excellent. Well, Professor Theo Hanein and Dr Wafaa Borja, that looks like a good place to wrap things up. Thank you both so much for diving into the topic of novel cements with us today.
Thank you for having us.
Thanks for having us.
As always, if you enjoyed this episode, please do make sure to rate, review, and subscribe if you haven't already done so. And if you're new to the World Cement podcast, please take a moment to check out some of our previous episodes too, where we've interviewed leading cement producers, industry associations, and other stakeholders on some of the key issues facing the cement industry today. That's all from me. Goodbye for now. I just wanted to take a moment to remind you to register for World Cement. It's free of charge and gives you access to the latest issues of World Cement, both in print and online. Every issue comes packed full of regional analysis, technical articles, project case studies, and the latest industry news. Simply head over to worldcement.com, click the magazine tab, and register today. It's as simple as that. Happy reading.